All right, we're going to go ahead and get started, please. I'd like to introduce Paulo Pagliari. I can't pronounce your name.
You got it.
Don't mind my Wisconsin accent. Paulo is an associate professor at the Southwest Research and Outreach Center at Lamberton, where he conducts research and also has an extension appointment. His research is focused on gaining a better understanding of the relationship between soil fertility status and soil biological processes and how these interactions affect crop yield on both conventional and organic cropping systems. So welcome.
Oh, thank you, Bruce. Yeah, you got the background pretty good. You must be reading my website or something. Good afternoon, everyone. Thank you for attending the event. I'd like to thank the organizer for the invitation to come and speak to you today. Are both cameras on? I'll try to look at the room and the cameras too. Okay. So yes, my talk today is about biological inoculation with nitrogen fixing bacteria to help improve nitrogen use efficiency in crops that are that don't have inoculation with rhizobia bacteria to improve nitrogen fixing. For example, your soybeans, your legume crops, they all can be inoculated with rhizobium and form nodules that will fix nitrogen from the atmosphere. Whereas our corn, wheat, oats, and barley, and all of the other grass crops, they do not have that capability. They don't form nodules. But there has been some work done with other type of bacteria that are not nodulating that can help maximize nitrogen use for those crops. And this is the talk we're going to be doing today, is about those particular bacteria. And they've been defined as one specific term. They're plant growth promoting bacteria. And we abbreviate that as PGPB, for plant growth promoting bacteria. And as I mentioned, they don't form nodules. They are free living soil bacteria. And they usually colonize the root rhizosphere. And then that's where all the magic seems to happen. There are many species of bacteria that fits their role that lives in the plant's rhizosphere. But we only have identified a handful of them. There are many more that we don't know that exist that are still in our soil and play a significant role. But I think we understand some of the major ones related to nitrogen and its importance to the plant biological systems primarily. Many of them are beneficial, but a lot of them are pathogenic, like your nematodes and some other diseases that live in the soil. They also colonize the rhizosphere, and that's how they do a lot of their damage. How does this bacteria affect plant growth? Usually, crop seeds are inoculated with this plant growth promoting bacteria. The seed will germinate, and then the bacteria will start to grow in the rhizosphere. And then as the plant grows and the bacteria colony grows, they will start exuding compounds that will benefit each other. Like the bacteria will start to secrete compounds like nitrate and ammonium, and then the plant is going to use that. And then as the plant grows, it exudates some organic compounds that feeds the bacteria in the soil, and that makes that colony grows better. And here is some example. As we have a small plant just germinating, we see here that the amount of plant exudates is really small and kind of seems to be fitting just a couple different types of bacteria. And then as the crop grows bigger, it can produce different compounds which will attract different microorganisms. And then as it grows even bigger, it can produce much more a wide variety of compounds that would then attract different microbes. And you can see that there's a bunch of microbes down here in your bulk soil. Which is not the rhizosphere, but then as you move into the rhizosphere zone, you can have some specialized microbes that will colonize that area and help with the nitrogen, not only nitrogen, but nutrient turnover that help the plant grow. So in a short summary, both of the plants and the microbes benefit from this partnership. As I mentioned, the plant creating all this food for the microbe as the root exudates is just throwing out a bunch of food there to serve as a way to bring the microbes that he wants close to it. And then as a trade-off, some of those plant growth promoting bacteria, they will, like I mentioned, will start to pull nitrogen from the atmosphere assimilate into nitrate and ammonium as forms that the plant can use, and then the plant will use those as it grows. Like I showed you before, there is a wide variety of microorganisms that can colonize the rhizosphere, and they're the ones that turn over many of the other nutrients. For example, phosphorus and sulfur also need to be mineralized before the plants can use it. And those are the microbes doing all of those mineralization from organic forms to inorganic forms. And so I'm mostly talking about the microorganisms that are related to nutrient cycling and provide nutrients to the plants. But there are also other microorganisms that fulfill other function within the plant, the rhizosphere microbial domain. For example, there are microbes that we know now that can help plants be more tolerant to heat, drought, and also insect damage. And that goes into the biochemistry of how some insects, some microbes in the soil can affect the production of hormones, certain hormones within the plant, and that can alleviate some of those other stresses that we see. But I don't know if there's much work in Minnesota that is being done with those other bacteria. I know that there's a lot of products that go into the nitrogen portion of this, and I have tested quite a few of them, and I will be telling you about those as we move on in the talk. And again, here to give a little more of a broader perspective here. So we have our bulk soil, and then we have this plant growing and sending roots and root hair throughout the soil profile. And then we have those microorganisms that are turning over nutrients. And then here are those compounds that I mentioned just before, where the microbes can start making the plant produce certain hormones that will help them be more tolerant to stresses. And there's also other interaction that could happen where some bacteria, like I said before, can colonize the root zone and start forming nodules. But that is not the case for the corn. That would be more for a legume plant. But there's also other interactions that can happen with the plant microbe in a system. And again, just to emphasize a little more how this all works, there's a lot of region between the root and the soil profile. And the root itself will modify the soil a little more. We create small areas where the bacteria could thrive better and also would serve as hiding spots from predators that will also predate in this bacteria. So the plant is really trying to maximize the function that the microbes can have, primarily in terms of providing some of the nutrients that the plant needs for growing. In our case, we're talking about a nitrogen-fixing bacteria. For example, here, the bacteria that we're going to be talking about is called the Zoospirillum brasiliensis. And the bacteria we have been testing is imported from Brazil. We have a special USDA permit to test the bacteria, and we've been using that for the past 2 years. But this particular bacteria is common in any soil. Any soil that plant grow, it will have the bacteria. So what's the point then in doing a seed inoculation if the bacteria are in the soil? Well, what happens is, like you see here, this soil, for example, has not been inoculated. And let's say that this bacteria here would be our nitrogen-fixing bacteria. There's only a few of them. When you have that small number of individuals in the community, they're not really going to make a significant impact. But then as we had that seed inoculation, then you can see now that you have much more members in that community. It's much bigger, and then the amount of products that's going to be putting out, like the amount of nitrogen that is being fixed, is much greater, and that's where we see the benefit from doing an inoculation. And again, here you have the bacteria. You would pull atmospheric nitrogen gas, which is pretty abundant. It would turn into compounds, mostly nitrogen, ammonium, and nitrate. And then they would excrete that. And then all of the microbes, not only the plants will be using that, but also all of the microbes in the rhizosphere would be benefiting from the secretion of these compounds. So now let's talk about some of the research work that we have done using this bacteria. The first, some objectives. We wanted to determine if the inoculation of wheat with some of those plant growth promoting bacteria would have a positive impact on wheat growth and yield. We also want to look at different inoculation rates to see what's best for Minnesota soils, and we had 2 locations for these trials. And we want to look at the soil inorganic nitrogen throughout the growing season as we do this inoculation to see if we can find any difference in the ammonium and nitrate in the soil. And then right now there's 2 studies that we have done with this bacteria. One is on wheat and the other one is on the corn. And then we'll talk about the corn after we look at the wheat. So there were 2 field trials that we did, one at Lamberton and one at the Crookston, and those were done at the ROC, the Research and Outreach Centers from the university, the Southwest and the Northwest. I was the one person in charge of managing the site at Lamberton, and then Lindsay Pease up at Crookston was the one in charge of managing that location up there. And as I mentioned, we had a nitrogen rate study where we applied increasing rates of nitrogen with 1 rate of inoculation only, was 4 ounces per acre of the inoculum. And this was a liquid compound that we mixed with the seed right before planting the wheat. And then we also had the inoculation rate where we put down 2, 4, 8, and 12 ounces of the product as the inoculation rates. And then we tested that 2 nitrogen rates, a 0 and a 50. So this way we could see if there was any change in the amount of nitrogen that was being fixed based on how much inoculation was done. At Crookston, because of the year we started and the rotation they had, we had to use a 3 rotation system in 2021. We had wheat after soybean and wheat after sugar beets for Crookston, and then at Lamberton we had the wheat after soybeans and wheat after corn, because we will see is there any difference when you're planting that wheat after a legume in terms of how much nitrogen is being fixed, or if you're planting that after a corn that is very intense in how much nitrogen is taken out of the soil. And then 2022 we had the same system in both locations. We took soil samples before planting to do a quick background check in terms of nutrient levels to see how much nitrogen we needed to plant for the crop, and also to look at phosphorus and potassium to make sure that those nutrients were not limiting. And then we took mid-season soil samples to look at ammonium and nitrate levels. As I mentioned, we want to see if we could track if the bacteria was really fixing the nitrogen or not. We look at grain yield and we collect grain samples for total nitrogen and protein content tests. Now here the weather graph. One of the main things that happened with these 2 trials that we did in 21, 22. Here we have the 21 soil data, and this is the available soil water. 2021 and then the 2022, you can see that there were, of the last 5 years, were the 2 driest seasons that we had at Lamberton. And then I think if you look at, I think 1976 would have been right down here with 2021. It was, I think we had about 7 inches of rain in 1976, and then 2021, I think we had 14 up to the end of the wheat growing season. In 2022 also, we only had like 10 inches of rain throughout the growing season for the wheat. So a lot of the moisture that we needed to really test the full effectiveness of this product wasn't there, but we were still able to see some positive responses, as you'll see. And there's some pretty interesting data too. So here is our soil nitrate for Lamberton after corn. We can see that as we put more nitrogen down and we have the inoculation, here we have the green bars are non-inoculated and the blue bar are inoculated, and the stars are where we see a significant response, and the y-axis is in parts per million. We can see that the highest rate, we almost had twice the amount of nitrate that was in the soil. And again, it could have been the bacteria, but the bacteria is not going to produce that much. It was kind of surprising to see all of this, because when we convert this back, it's about 50 pounds of nitrogen, and half of that, 25 pounds, would have been from the bacteria. So it's quite a bit of nitrogen. And then when you look at the wheat after soybean, we also saw a big increase there. Again, almost 60 pounds of nitrogen. And as nitrate, and was also higher than the control where there was no inoculation. And we see that at the lower rates, there's still this trend that was a little bit higher. So it could be that there is something going on where there is some nitrogen being fixed by the bacteria. And then when we look at grain yield for Lamberton, here we have wheat after corn. We found that there was a significant response here in the control. And interestingly, we only saw a nitrogen response from this first jump right here in the non-inoculated. And then there was no response to even a nitrogen rate. And this was, and you can see the yield, the two are pretty low. And this is, again, that dry season coming in, not have enough moisture for the plant to express its full potential. And I think that's why we are not seeing a lot of responses. But again, at the control here, there was a response. And then when you grew a soybean, you found two positive response. We found that a 0 and the highest nitrogen rate. Again, no nitrogen response, but we did see some positive responses to that inoculation there. Now for Crookston, very similar, very dry conditions at Crookston as well, and very similar results after the soybean. We saw the response in the control, but after 30 pounds of N were applied, no more responses to N. And then if we look at the nitrogen rate, nitrate levels in the soil, I said it's about 30 pounds, right? 25 pounds of nitrogen being fixed. And when you look at the responses, it's about what it was, about 30 pounds maximize the yield in most of the cases. And that seems to be what we are getting as nitrogen fixed from this bacteria under these dry conditions and the growth of wheat. So when you look at some summaries, that yield increase was about a 15% response was observed when you saw that positive response to the bacteria inoculation, no response to nitrogen at Lamberton, neither at Crookston. And the soil nitrates at Lamberton were up to 111% higher than where we saw that inoculation against non-inoculated. And then at Crookston, we did not see much for a soil test difference in nitrate or ammonium. And again, we did not see any difference in ammonium for Lamberton either. And the only difference at Crookston was that control plot. They had a really good response. Again, it was about 15% increase in yield with this inoculation. Now for 2022, we actually had a little less moisture throughout the growing season than 2021. And here the response is a little bit different. We saw in the ammonium now seems to be responding to this inoculation. And we found a positive higher ammonium at the highest rate. But then when you look at the wheat after soybean, it was the opposite. The non-inoculated plots had higher ammonium in the soil than the inoculated plots. So I'm not sure what is this effect there. And again, you can also see that if we were to compare among rates, there was much lower ammonium in here as well. It could have been converted to nitrate, but there was no nitrate differences for 2022. And no location showed a positive response to inoculation or nitrogen rates. So it was really dry. The plant really didn't show its full potential at all. There wasn't much growth, and it was a very unfortunate year to do it. So hopefully this 2023 will be a regular season, and we'll be able to see the full potential of this work. Now let's look at the corn. So the wheat trial was funded by the Minnesota wheat growers starting 2021, and then they funded again in 2022 and also in 2023. And then the corn trial was funded by the corn growers last year, and I have submitted a proposal again to look at the trial for the corn again in this year, hoping that we have a better season. Now here for the corn is a little different than what we saw for the wheat. We found that non-inoculated plots were having higher nitrate and ammonium levels than where the inoculation plots were. I don't know why this would be, but I'm thinking that it could be because of the drought that we had, and the yields of corn were really low. Our yields are usually on the 200 bushels, and here we can see that we were at just over about 150. So it was really low, and I think the crop just was not able to take up all the nitrogen. But then when you have that inoculation, there should also be the nitrogen in there. And what I think it could be happening is maybe some of the other microorganisms are using some of the nitrogen, because there's probably a more diverse microbial community in the soil that can probably make use of the nitrogen. And so we are not really finding it in there, because if we were to leach, we would have found the leached in both plots, not only where it was inoculated. So maybe there's something else going on in terms of microbial use of nitrogen as well. And then here's just a sum of ammonium nitrates to give a better idea of how much nitrogen was in there. And again, this is in ppms, you get in pounds, you multiply that by 2. So almost all the nitrogen that I put down was still in the soil. It really was a dry year, and the crop really, maybe about half of its yield potential came out of that field, because it was a really good field too. And again, here we saw one positive nitrogen response, which was for non-inoculated trials here, the green bars. The highest yield was at 100 pounds per acre. Whereas for the inoculated plots, at about 50 pounds of nitrogen, we saw maximum yield. So it's about 50 pounds of nitrogen we can assume was provided by the bacteria inoculation, which is pretty good. And again, if it was a drier year, we would see those bars here go up to 200, 220, and then that would be much easier to see the potential for this work. But again, seeing this over here, where the inoculation was able to bring this bar up to the same rate as 100, is right in line with the work that we have seen in South America. With all the work I've been collaborated with people in Brazil, that's what they see. They see about 25% of the nitrogen needs reduced when they're using this inoculation in corn, which is about 50 pounds of nitrogen. And this is what we found here. It's not 50%, it's 50 pounds. It just happened to be 50% in this case for maximum yield. But that's what I'm hoping that we can get with this type of work, that about 50 pounds of N can be provided to a corn crop. So again, we found that there was one positive response there, where the inoculation was able to bring it down 50 pounds of nitrogen to get maximum yield. And we are doing some nitrogen analysis. We have been having some issues. The nitrogen analyzer we have runs on helium, and there's been a lot of helium shortage. It's been very difficult to get helium gas to run instruments this past year. But now we have it. We are in the process of analyzing those samples. So hopefully we'll get those results by the end of the winter here, and we can start putting some more summaries together. Like I mentioned, in Brazil, it's about 25% of nitrogen demands from the crop is being met with inoculation. And there's some other trials too in Africa and some of the Asia countries where they're using some of this nitrogen fixing bacteria, and that's also about what they're seeing. Up to 50 pounds of N is being able to be provided by the bacteria. And again, we hope that when we have adequate moisture, then we're really going to see this potential to be fully realized. Because when you have a drought, then it makes it very difficult to test, especially when there's no response to nitrogen. Then how do we really know, right, what is going on? And again, the wheat growers are interested in continuing the research. I think it's pretty good results given the considerations of weather. Again, the corn growers are looking at the proposal now, and I'm hoping that they will also be able to continue the work for another year. We're able to secure funding from FRAC to look at this type of work with dry beans. We're going to be testing a very similar work that we did for the wheat on the dry bean at 2 locations, one at Lamberton and one in Becker. So we're going to have some irrigated land in case we got a drought again. Then we're going to at least have one location with rain irrigated conditions that we'll be able to really look at this potential and not be relying solely on weather. And we have also started to work with a strain from Minnesota, because again, this strain is from Brazil and might not be the best to work with for Minnesota soil. So we already did some isolation of bacteria, and we're starting to look for more funding to continue to look at getting a bacteria from Minnesota that would be more adapted to Minnesota climate and maybe be even more effective than these strains from Brazil. Now, one of the questions that's probably going on your head is, are all these products the same? There is a ton of products that are out there that claims to do all of this work. And I personally have tested at least a dozen of those over the last 10 years in my career. And I've been very skeptical because every product I tested never worked. I never see one positive hit in terms of finding a good response and increasing yield. It's always the same as the control. And it's been the case. And I've tested seed treatment. I tested powder that you mix in a water and then you spray on the soil. I tested solution that you spray on a growing plant. I tested manure, tea. You ask my technical support people, they are tired of me testing all this crazy stuff and never find anything. We start to label those things as pixie dust. This is what we refer to them in the lab because we never really found a response until I start working with this folks in Brazil. I can be very, very skeptical. I'm like, I'm going to partner with you guys, but I know what you're going to find. And then when I start looking at their data, I'm like, okay, won't you send me the real data so I can do some of my analysis instead of just looking at tables? I want to really do the analysis myself. And then I started seeing that, okay, this is different than what I've done before because there's a real response here. So I had a student that came up in 2019. He worked in my lab for a while, and then he and I developed this protocol for the wheat. And then we started that work in 21, and then we saw some responses. I'm like, well, maybe there is something to this. So let's do a little more work. And so far, it's been, I think it's been pretty positive. And then here's some of the other work that we are doing down in Brazil with this type of bacteria. Here we have a control treatment that had no inoculation. And then we have different types of inoculation. And then over here, you can clearly see that those plants are much healthier. And this is, again, it's the same bacteria as Zospirillum, but there's also another bacteria in there that is helpful with disease, root diseases in soybean in Brazil. And it's really showing to be, you can see the picture, it really shows that it's very effective. So with that, I would like to open for questions. It is, yes, it's trichoderma. Is there people online that can ask questions too? Oh. Okay, yes, the corn trial, when were the nitrogen application made? We usually do it right pre-plant. We put all the nitrogen before planting, and then we inoculate the seeds, and then we go and we plant the corn. Okay. The cost in Brazil, so because of the conversion, I think right now it's about $1.25 per acre for the product. So yeah, it's really cheap. But I think here in terms of the US, what it could cost, I don't know, but I don't think it would be more than $2 to $3 an acre for this type of material. The inoculant, the bacteria is called the Zospirillum brasiliensis. Now the product name, I don't recall it. I have a picture here. I don't know if it has the name. Let me quick look for you in case you want to look it up. It is called Master Fix. Yeah, it's called Master Fix is what we used. What did I say about trichoderma? We, in Brazil, not in the United States, the same group of scientists in Brazil that I worked with the Zospirillum only, now we start doing some work with trichoderma and Zospirillum on soybeans. And it's mostly for health. It's not for the nitrogen needs because soybean doesn't need any additional nitrogen fixing bacteria, but it's more for disease control. Like I mentioned, some of those bacteria have a wide range of benefits that they can bring to the plant. And being able to cope with the stress, especially disease stress, is one of them. And trichoderma seems to be a very, very good bacteria for some of the root diseases that are starting to be an issue in Brazil. Okay, so what I mean by they don't work, and this is referring to some of the other products. So yeah, let me be more specific. I think how this work is done is we get a soil and then we can isolate the bacteria from the soil. And then the first step is to see if the bacteria is going to fix nitrogen from the atmosphere on the growth media. And then you do that, and then the bacteria will fix nitrogen. right? And then you have a positive. Say, okay, this bacteria fixes nitrogen, so it's going to be a good candidate. But this is just the first step. You have to have maybe a dozen of those bacteria. Like, for example, now we have 7 strains that we have isolated, and once you have more funding, then you can start doing the next stage. And I think that's how companies do it as well. They find the positives, and then they might do, the next step would be to do a soil incubation and then see if you find a positive where you're finding the bacteria is also fixing nitrogen with soil, and then we add the plant. Then you do that in a greenhouse, and then also you have a few candidates. I would say out of a dozen, you might have 2 or 3 that you take out to the field, and then you do a final field trial, and then you might have 1 that works, right? 1 or 2. And what I say that they don't work is when you take those to the field, they might be fixing nitrogen, but they are not fixing enough that the plant is getting a benefit from them. And that's what I saw in all of the work that I have done previously is the companies come to us and they say, we have a product, it works, but it only works in very marginal land. And I think, well, anything works in marginal land, right? So when you test this in a land that is somewhat productive and you're looking at minimizing your inputs so that you get a benefit from that's already being good, and then you just add a little bit of a boost in there to help you maximize its ability to provide the crops with the nutrients, then that's why I say they don't work, because you never really saw a positive response. Now, I think the question was also talking about emissions. Then those questions, I don't know, because we haven't really gone into looking for if there is nitrogen coming off the soil as nitrogen gases, and if there is higher emissions or not. Yeah, no, the test in Brazil, it's what we do is nothing in virgin grounds. When you go to the field trials, it's all farm field or experimental research stations like we do here in the US. So it's always looking at real field scenarios, because if we are looking at making this and make this a commercial product, we do not want to be testing this in land that is not used for commercial production. We want to be sure that this works on soil that is going to be used for commercial production of grains. Yes, trichoderma is a fungus. Now, you would harm if there is fungicide in a seed. Yes, a lot of times for the bacteria, there is no issue because it's a different species. But with the fungicide, you would be affecting the fungus. So when we do this trial, then we're looking at seed that is usually not treated with a fungicide. Then we'll do fungicides application later on when needed. But again, we are looking for microorganisms that are helping cope with the disease. So we want to see the disease come in, and therefore we do not want to be putting a lot of those fungicides, because if you put the fungicide, then you don't know if the disease is going to be strong enough to cause a dragging yield, and then you never know if the product works or not. So we do want to see that bacteria there, the fungicide not applied, to see that fungus grow and give the response. Yes.
For the statement that manure is the original inoculant, is that accurate or way off?
No, it is. Manure does have a lot of, yeah. The question was if manure is the ultimate inoculant. And manure does have a lot of benefits. It does have a lot of microorganisms that help the soil, but they fulfill different needs, right? Like a manure has, I don't know how many species of bacteria in there, and they are not specialized. Here we're talking about, like I showed you in one of those examples, right here. So you have, like, this is what the manure kind of would be like. There's all those different microorganisms and a lot of nutrients already in there. But what we are doing with this specialized bacteria is we are really growing the number of one particular species of bacteria that has one very specific function, which is bringing nitrogen from the atmosphere and making to nitrogen that the plant can use. Now, there probably is some of those bacteria in manure as well, but their number will not be large enough to cause this positive effect, right? Yes.
Have there been anything to see if there's a year after effect that the bacteria survive and inoculate in the second year?
Yeah, the question is if we have done any work to look at potential residual effect of the bacteria in the soil. And we have done, not in Minnesota, back in Brazil we did when we first started. But like I mentioned, the bacteria is already in the soil. And then once the plant dies, you harvest that plant, then you're not producing those root exudates. And then the bacteria also tend to decrease the population number. So they will die down to their background level. So this is something they have to do every time you plant a crop. You have to boost that specific type of bacteria that will give you the nitrogen. So there's no residual, unfortunately. It's not like rhizobium that stays in the soil and sometimes you don't need to inoculate.
Very good.
All right,
Let's
thank
give
you,
him a
everybody.
hand.
Thank you, Bruce.
Very good. Thank you, Paulo.